Hi, my name is Russ Cox. I'm a software engineer at Google in Cambridge, Massachusetts, and I work on the Go programming language. I gave a talk last week at the Boston area Google Developers Group meeting, but the recording had some audio problems, so this screencast is a re-recording of that talk. So what is Go? Go is a new open-source programming language that we've developed at Google over the past 4 years. It's a concurrent, garbage-collected language. And the primary motivation for doing a new language was to create something that can handle the scale of programming that we have at Google, both in number of lines of code and number of engineers working on the code. Another important kind of scale is the scale of the interconnection between programs. We build large, distributed systems that connect thousands or more machines, and it's important to have a language that supports the kinds of problems you encounter writing those kinds of programs. Another answer to the question, what is Go, is that for me, Go is a fast, fun, and productive language for writing programs. I'm having more fun writing Go programs than I have writing programs in any language in a long time. And I can write the programs quickly, they build quickly, I have fun doing it, and I'm incredibly productive. This talk is a tour of 3 pieces of Go that I think are essential to it being fast, fun, and productive. Those 3 pieces are Go's approach to interfaces, Go's support for reflection on types and values, and Go's support for concurrency. I've tried as much as possible to illustrate those pieces with real code, so while we'll see some simple example programs, we'll also see how those important parts of Go are used in the standard library. I think I've talked long enough without showing you any code, so here's our first Go program, Hello World. And the first line of the program declares that this program is in a package named main. And the second line imports another package, named by the path fumpt, and the last 3 lines declare a function named main. And the body of this main function is a single function call to the printf function in the fumpt package, or fumpt.printf. The argument to fumpt.printf is the string hello world. And you'll note that world is written in Japanese. Go uses Unicode and UTF-8 throughout, and in particular Go's source text is defined to be UTF-8 encoded. So all Go programs start in the package name main, running the function name main. So if we run this program, sure enough it does what you'd expect. Now I'm not going to give a full introduction to the language in this talk, although I'll try to explain the pieces you need to understand the examples. If there's anything you don't understand or you want to learn more, I suggest visiting tour.golang.org, which is an interactive introduction to the language, or reading the language spec at golang.org. So on to this tour. The first part of Go I want to talk about are interfaces. Now in Go, a type implements an interface by defining the required methods. I want to show you a simple example of what that means. Here's a variant of our Hello World program. Fumpt.printf is named printf because just like C's printf, you can write a format string with a %s and pass a string argument where the %s goes. And so I should point out that I've dropped the package declaration and the import statements, but they're still required, they're just off the slide. So if we run this program, it still prints Hello World. The interesting thing about this though is that %s will print things other than strings too. Printf defines, in fact, that %s can be used to format any value that has a method named string with no arguments that returns a string. And so in this program, I've defined a new type, world, which is an empty struct, and it has a method that returns the constant string world. The syntax at the bottom defines a method, which is a function introduced by the func keyword, with a receiver, which is the parameter list that immediately follows func. And the receiver variable here is w of type pointer to world, and then the name of the method is capital string, and there are no arguments to the method, indicated by the open and close parentheses, and then it returns a string. And so when we pass a newly allocated world value as %s's argument, printf prints, surprise, hello world. How does it know to do that? How does the new world argument turn into that string? Package fumpt defines an interface called stringer, which, as you can read in the doc comment, means that any value with a string method with this specific signature will cause %s to call that method to obtain the string to print. These code snippets, by the way, are being pulled out of the source code by the slide software. But you don't have to read the source code to learn this. You can also read the generated documentation on the web at golang.org. The name stringer gives a convention in Go. When we have simple one-method interfaces, and there are more of them than you might first expect, we name them by taking the method name and adding an ER suffix, like stringer, reader, closer, or marshaller. Let's look at a slightly less trivial example of a value with a string method. Here I've defined a new type named office, whose representation is an int. And you can think of that type statement as sort of like a typedef in C. There's no boxing of the int or anything like that. An office is an int, except that it does create a separate type. The office's representation is int, but office and int are not interchangeable in your program. The next few lines define some constants of type office. The equals iota here creates something like a C enum, and so Boston has value 0 and New York has value 1. And then I define a string method for office, which returns Google, comma, and then the name of the office looked up in an array that's off the screen. One interesting thing about this string method is that it's a method on an integer, not on a pointer to a struct. This is one of the nice generalities of Go, that you can define methods on any data representation, unlike in other languages like C++ or Python or Java that essentially restrict methods to the logical equivalent of pointers to structs. And then if we pass Boston to printf's %s, the %s calls Boston's string method, which returns Google, comma, and then the office place. So the whole output is hello Google, Cambridge, Massachusetts, which is where I gave this talk. I did promise to use code from the libraries, so here's an example of the same thing we did with Office, but in the standard library. The time package has the concept of a weekday, and in Go, like in C and other languages, the weekday is an integer. 0 is Sunday, 1 is Monday, and so on. But it also has a string method to print the human readable form. And so this program prints the current day of the week twice, once with %s and once with %d. And we can see that it prints Saturday and 6. Here's the actual code for weekday in package time, pulled right from the sources. The definition of weekday is an int, and then the predefined day name constants Sunday, Monday, Tuesday, and so on. And here's the full method implementation. There's an array of day names, and then the string method returns the right element from that array. And that string method is what allows Printf to print the value 6 of type weekday as Saturday instead of as 6. Of course, printing the name of an enumeration is not all that interesting. We could have just built enumeration printing into the language, but having the generality of a string method lets us do more interesting things. So here's another type from the time package. This one is called duration, and it represents the elapsed time between two instants in time. And the representation is an integer number of nanoseconds stored in a signed 64-bit integer. And so here we have the type definition and some constants. A nanosecond has type duration and value 1. A microsecond is 1,000 nanoseconds, and so on. I'm not showing the string method, but it does have one. Let's print a duration. Here we have a program that records the start time and then fetches the content at google.com, and then it prints the elapsed time. Time.Since returns the duration that has elapsed since its argument, which is the start in this case, and then we pass that duration to println, which is like printf but without the format string, and it adds a new line. And if we run this, we see it prints 580 milliseconds, and now that things like DNS are cached, 190 milliseconds. And note also that it prints ms for milliseconds because this is a millisecondish time. It's less than a second, it's more than a millisecond, and so it's chosen to print it in milliseconds. If we were to print a larger time, suppose we add an hour to the time, we would get different units. So here we have 1 hour, no minutes, and 0.187 seconds. And of course we can also change it to print with %d. The most important thing about these examples is that there are no implements declarations in this code. These types, and we've seen world and office and weekday and duration, they don't declare that they implement fump.stringer. They might not even know that fump.stringer exists. But because they implement a method named string that takes no arguments and returns a string, they do implement fump.stringer, and so fumpt can print them. This is a key difference compared to interfaces in languages like Java and C#. Being required to give the implements declarations means that in those other languages, people tend to use interfaces only for more heavyweight concepts. And it also introduces dependencies between packages that might otherwise not exist. For example, since package time is the only way in Go to get the system time, it needs to be treated as very low level, nearly a leaf in the package tree. It's not okay if using package time implies the use of some other large utility packages like fumpt and all its dependencies. And in Go, it doesn't. Package time's types like weekday and duration and even time implement fump.stringer, even though package time never mentions fumpt in its source code. Another important reason not to have implements declarations is that you can notice patterns after the fact and write interfaces to describe them without having to go back into the packages and annotate their types to say explicitly that they implement your new interface. Maybe you're just a user and you noticed a pattern in the standard library and you want to create an interface that captures that. In that case, going into the standard library and making changes isn't even an option. But in Go, you don't have to, and you can still use these interfaces. And in fact, many of the interfaces even in the Go standard library started out this way. capturing idioms and patterns that just arose organically. And one such example is the writer interface. Package io defines an interface called writer, which, as you might guess, is a one-method interface with a write method. This is the write method that an operating system file might have. For the Unix programmers, you can think of it as corresponding to the write system call. This write method takes a data block to write named p of type slice of byte. You can think of slice as a variable-sized array. And it returns two values, the number of bytes actually written, and if that number is less than the length requested, an error explaining what went wrong. As I mentioned, the canonical implementation of the writer interface is an operating system file. And this is, of course, one of the key abstractions in Unix. In Unix, the abstraction is represented by a file descriptor, and in Go, the abstraction is represented by a value that implements io.Writer. The FOMP package has a function called fprintf, which is, of course, named after C's fprintf, but the first argument here, instead of being a file, is any io.Writer. In this program, we do pass a file, os.stdout, for standard output, as the io.Writer, and the message we write to that file is boringly hello world. The nice thing about the writer interface, of course, is that you can substitute implementations besides operating system files. For example, hash functions in Go are conventionally presented as writers. In this example, the crc32 package's new IEEE function returns a new IEEE crc32 computation, here assigned to the value h, and that value is itself a writer. And so we can write the string hello world to it with fomp.fprintf, and then we can retrieve the hash of the written data by calling h's sum32 method. And here's the 32-bit CRC of our hello world string. We can also go meta and implement writers that wrap writers. So package io provides a function named MultiWriter that takes as input a variadic list of 0 or more writers and returns a single writer. If you write to the returned writer, the writes are all broadcast to all the writers in the original list. And the function body here returns a new struct of type multi-writer containing a single field that it initializes to the writer list. Then the multi-writer's write method loops over the writers in the list and calls each one's write method. If any of the writes returns an error, then the multi-writer returns that error. Otherwise, the write eventually returns successfully. Now in this example, we build a multi-writer that writes to both h, the crc32 function, and standard output. The fprintf to w here writes hello world to both of these, and so we can see the message on standard output, but we can still retrieve the checksum of the bytes by calling sum32. So I want to give you one final example of a writer, and then I promise I'll stop with the hello world examples. Package hex provides a function called dumper, and if you call dumper with a writer w, then dumper returns a new write closer. That's something with the standard write method, but also the standard close method that you can write things to. And when you write data to this write closer, the underlying implementation writes a hex dump of that data to the original w. The close method here is needed because the hex dump prints one line at a time, and close signals that no more data is coming, so if there's a little bit of data left over, it should print that last line. So here's our last hello world program. We create a new hex dumper h that writes the dump to standard output. We queue an h.close call to be run when main returns, that's the defer statement, and then we fprintf hello world into h. And sure enough, that prints a hex dump to standard output. So the obvious complement to the writer interface is a reader interface, and we have one of those too, obviously modeled after the Unix read system call. There are many examples of implementations of reader, but I'm not going to show any of them to you in detail. An operating system file is obviously a reader. The buffered IO package defines a reader type that is a buffered version of an underlying reader. A network connection is a reader and also a writer. Data transformations and encodings like gzip compression or TLS encryption are presented as readers and writers. And then there's a very commonly used type called bytes.buffer that's a simple in-memory byte buffer that you can write to and then read back from. Now I started working on Go in late summer 2008, and the Go standard library at that time was minuscule. We had operating system file I/O, and that was about it. And one of the first packages I wrote was the buffered IO package, buff.io. And I had to pick what buff.io buffered. And so I was lucky enough to be the one who got to define these two types, io.reader and io.writer. And it was important even on that first day that the one existing implementation, os.file, didn't have to declare that it implemented io.reader and io.writer, because package io needed to import package os for another definition. And if package os had also imported io in order to write the implements clause, there would have been a cyclic dependency. Now, there was just the one implementation, os.file. Of course, the second implementation was buff.io.reader and buff.io.writer, and the third implementation, network connections, came a week later. And looking back, these interfaces seem inevitable, but they weren't obvious then. It was a big aha for us, and it was a lot of fun when we realized how general these were going to be and how productive these were going to make Go programmers. But not everything is possible to do with interfaces, and I want to close with an example that doesn't use them at all. This program defines a new type, lang, which represents a programming language. A lang is a struct with 3 fields, a name, which is a string, the year the language appeared, which is an int, and the URL for the language's homepage, which is also a string. And here the main function creates a new variable named lang, of type lang, and it initializes the 3 fields to the string go, the int 2009, and the string golang.org. And then it calls func.printf to print lang. It uses the %v verb, which we haven't seen yet, but means v for value. And you can pass any data you like to %v and it will print a reasonable representation. So here it prints braces to indicate a struct and shows the 3 fields. So how does this work? Clearly not with interfaces, since there's not a string method in sight. So this takes us to our second topic, reflection. In Go, reflection means that the implementation makes type information and basic operations on those types available at runtime. So if you have an unknown value, you can find out its type, the definition of that type, and perform the type's basic operations on that value. Before I go on, I want to say something important. I've never talked about reflection in Intro to Go before, and there's a reason for that. When it comes to reflection, a little bit goes a very long way. And I've seen first Go programs in which every line is doing something with reflection, and that's usually an indication that the program is not using Go as well as it might. Now there are definitely times when reflection is incredibly useful, and we're going to see some of them, but if you find code that uses it in every program instead of in 1 or 2 key places, then I would argue that that code is probably doing something wrong. And so just keep that in mind as you read other people's Go code and write your own. Back to the code. Here's a simpler printf than the one we ended the last section with. Print is like printf but without the format string. It just prints the list of arguments using %v for all of them. And so this program prints hello 42. Now the most important fact about print and printf and so on is that they are not magic. They are not built into the language. Of course, printf is not built into the language in C either, but in C it's unsafe. And in safer languages that have printf, it usually does end up being a built-in in one way or another. And we knew we didn't want to do that for Go, that we'd have done something wrong if you couldn't write printf as ordinary Go code. It just wouldn't be acceptable for print and printf to be magic. But of course there has to be magic somewhere, and what we did is package up that magic into a package called reflect that provides the functionality that printf needs. Here's our same hello 42 program, but I've changed it from saying func.printf to myprint, and then we have an implementation of myprint at the bottom. So myprint takes a list of 0 or more arguments, that's what the ... says, and the arguments all have type interface open brace close brace, which is an interface type that requires no methods at all. So in Go, remember, an interface is satisfied by any type that implements all the required methods, and since there are no requirements, they are met by every possible type. And so here, myprint loops over the arguments, and for each one it executes a switch statement. The first thing the switch statement does is execute this assignment, v equals reflect.value of arg, and that creates a new variable v, initializes the result of the function call, and reflect.value of returns a reflect value, which has a kind method that you can use to find out what kind of value was passed to value of. And that's exactly what the switch looks at, v.kind. And so if the kind is reflect.string, then myprint fetches the underlying string by calling v.string, and it passes it to standard output's writeString method. If the kind is reflect.int, then myprint fetches v.int, the underlying value as an int 64, and it calls strconv.formatInt to turn that into a decimal string, and then it writes that string to standard output. And so if we run this program, it prints hello 42, just like the other one. Of course, this baby print only prints strings and integers, but to add other types and get a more full-featured printf, it's just more of the same. In particular, if the kind is reflect.struct, then there are more questions you can ask the reflect package to find out the names and types of the struct's fields, and also the values of the fields in the specific value v. That's how printf was able to print the lang struct in the earlier example. Here's that example again. And there are some variants we can get by using different flags on the %v. So we can use %+v, which prints a slightly more detailed version, or we can use %sharpv, which prints the alternate syntax for the printf verb. In Go, %sharpv, the alternate syntax is actually just Go syntax. So if we run this, we'll see that %v prints the braced Go 2009 and golang.org. %+v adds struct field names to it, so we see name : and year : and URL : and then the %v has printed the actual Go literal syntax, including a package name on the type, so we have main.lang and then the Go syntax for constructing that value. I made the point earlier that we knew from the start that printf shouldn't be magic, that the kind of tools you'd need to write printf might be useful in other contexts. It was a lot of fun to discover what those other contexts were. So for example, if you can print a struct like this in the human readable notation, it's not a big leap to adapt that code to print in other formats, and you can see a hint of that here in the %v, which prints Go syntax. But here's another example, the same program, but I've replaced fump.printf with the JSON package's JSON.Marshal function. And JSON.Marshal is essentially printf, but it prints JSON notation. And so here the JSON package uses the same reflection capabilities to print a valid JSON encoding of the data. And notice that we didn't have to write any special code for the lang type or hand the lang type to any kind of preprocessor or other tool. The JSON package just gets a value of type lang and turns it into sensible JSON. There's nothing special about JSON, of course. So here we've changed one line that called JSON.Marshal into a line that calls XML.Marshal indent. And of course it prints indented XML instead of JSON. So now we've seen 3 different ways to convert data to output. Fump.printf's %v converts data structures to human readable text, JSON.Marshal converts data structures to JSON, and XML.Marshal converts data structures to XML. There's nothing special about turning data structures in memory into encoded text, though. We can use the same techniques to turn encoded text into data structures in memory and reverse the process. So I want to show you an example of reading JSON from a file. Here's a simple program that opens a file with some JSON inside, and then it calls io.copy to copy the input file to standard output. Now, io.copy is a nice little function on its own. It takes an io.writer and an io.reader, and it does the obvious thing. It's like memcopy, but for io. So let's run this. So we've basically implemented cat, and here's the file contents. You can see that it's more information about programming languages. That's the JSON that I wrote by hand. So next, let's decode it. To do that, we're going to replace the io.copy call, and instead we copy JSON.newDecoder to create a decoder that reads from the input, and then we loop decoding each value into a lang and stop at EOF. And when we do get a lang, we print it with %v. So if we run this, this is printing the same data that was in the input file, but now we're printing it by decoding each of the values into a lang struct, and then pass that struct to printf. Now notice there's no special code for the lang type. The JSON decoder is just running the inverse of the encoding process. Now I want to write a bunch of programs that process this input, and I don't want to write this loop over and over. So if you bear with me for a minute, we're going to refactor this code to be a little more general. I changed 2 lines. The first line used to say funcMain to define the program's main function, and now it's funcDo to define a function named do. And that function, do, takes one argument, a parameter f, that is itself a function that takes a parameter of type lang. And then at the bottom of the code, where we used to call fump.printf, we call f on lang. Again, here's the old code. And then we change these 2 lines to abstract the input reading into this do function. But we lost our main function, so we need to write a new one. So let's make the program do the same thing it did before, namely print the lang struct. So this program calls do, you can see the function call, and the argument to do is a function literal, an anonymous function, a lambda, a closure, whatever you want to call it, that takes a lang argument and prints it. And so when we run this, sure enough, it prints the input we were reading. But now we've got room on the slide to do some more interesting work. So maybe someone walks in at this point and says, they want that data, but they need it in XML. Well, that's easy. Let's print it in XML. This program is the same as on the previous slide, except just like we did earlier, we replaced the printf with an XML.Marshal indent to print marshaled indented XML. Now notice that we defined the lang type and its 3 fields, but we did nothing else to explain how that data corresponds to JSON or XML decoding. The JSON and XML packages use reflection to give us decoders and encoders, and this program does both of these operations. It's a JSON to XML converter with no work on our part dealing with explicit JSON or XML trees. This is one of my favorite uses of reflection. I wrote the XML package originally just for decoding XML, to write an XMPP internet chat package to connect to the Google Talk chat service. If you're familiar with XMPP, you know that it encodes the chat messages in a stream of XML encodings, and most code I've seen that deals with XMPP has a significant chunk of logic to pull the relevant pieces out of the XML. With this XML package, though, my Go program just defines a data structure for each message, just like lang, and then it reads each XML block into the appropriate struct type. And the struct specifies which fields the client cares about and what types they have. And I didn't have to do any manual XML decoding. It was fantastic and it was incredibly productive. Getting back to our input, here's another thing we could do as we read the input file. We could write a toy web crawler. So each language has an associated URL, and we could fetch that URL and count how many bytes are served for each language's homepage. So here we call the count function with the language name and the URL, and we've wrapped the do call in some code that times how long this takes, just like when we timed how long it took to load google.com earlier. So this is function main. Here's the actual count function. It calls http.get to get the URL, and then it calls io.copy to copy the body of the response, r.body, to a writer we haven't seen before, ioutil.discard. ioutil.discard is the dev null of io.writers. It takes whatever you give it and throws it away. But one of the things io.copy returns is the number of bytes it copied, so that's the number of bytes in the response. So we end by printing the name of the language, the number of bytes on its homepage, and the amount of time it took to do the HTTP fetch. So here you can see that the various languages have websites of various sizes that take various times to load. You can see that here Python took half a second, Ruby and Scala's websites each took about 2 seconds, and Go also took half a second. And so the total was 5.5 seconds, which is unfortunate since no web page took longer than 2.25 seconds to load, but the crawler ran for twice that. If we could run those fetches in parallel, we could speed the crawler up quite a bit. And so that brings me to the next topic, Go's support for concurrency. I want to make a distinction here between parallelism and concurrency. Parallelism is running multiple things simultaneously, and concurrency is a way to deal with multiple things simultaneously. And so one way to think of it is that concurrency is the coordination of parallel computations. So Go provides Go routines to let you run multiple computations simultaneously, and Go routines create parallelism. But Go also provides channels to let you coordinate these parallel computations by explicit communication. So here's the same crawler we had built by the end of the last section, the one that loads pages one at a time, one after the other. I'll just run it one more time. So we want to overlap these page loads, and so we turn to parallelism. To introduce parallelism into this program, we insert the word Go before the call to count. This makes the call run in its own Go routine. So at the end of the call to do, we've created one new Go routine for each language, and all their HTTP fetches are running in parallel. You can see that they finish a lot more quickly. There's only one problem with this program. We created all this parallelism, but we don't have any coordination of it. So we have no way to know when the fetches are done. I've put a sleep at the end of main here to let them finish, but now the program runs for 10 seconds before it exits. So obviously we need to coordinate this parallelism, and we do that with channels. Here's the count function. The same one we saw before, completely unchanged. Now to make it concurrent, I'm going to change it ever so slightly. Here I've changed 3 lines. First, the function has a new argument, a parameter c of type channel of string. The left arrow is the Go communication operator, and the fact that it's pointing into the word chan is an annotation declaring that the only allowed operation is sending to the channel. I've also changed the 2 calls to printf. They now call sprintf, which returns a string, and then the code sends that string to the channel using the left arrow communication operator. And then we need to change main to call this adapted function. Here's the old parallel main, and here's the concurrent one. The new lines of code here create a channel of strings c and initialize a counter n to 0. And then the function literal that do runs for each language passes c to each new Go routine and increments n to count the number of Go routines it's created. So after the loop is done, instead of sleeping for 10 seconds, this main runs a loop from 0 to n. And each iteration of the loop reads one result from the channel and prints it. Since each Go routine prints one result, once the loop is done, we know that all the Go routines are done, so we can exit by returning from main. There's no sleeping required. We know exactly when we're done. Now I've added the timing code back so we can tell how long main actually runs for. So that's pretty good. Main ran just as long as the longest fetch. That's impressive. We got them all to run in under a second. Suppose that we don't want to ever wait longer than 1 second for these pages to come back. We just want to give up at that point. So we can do that by using the time.After function. It takes as an argument a duration, here 10 seconds, and it returns a new channel. And it also promises that after the given duration has elapsed, it will send the current time to that channel. So now, on each iteration of the loop, instead of doing the receive and print, we now use a select statement. The select statement is like the switch statement, but the cases are communication operations. Here, the first case is that we might receive a result from the channel C, and if that happens, we print it. The second case is that we might receive the current time on the timeout channel, which means the duration has elapsed and we've timed out. And if that happens, we print that we timed out and we return from main, which will exit the program. So each time we run the select statement, it blocks until one of the cases can proceed, and then it runs that case. So each iteration essentially makes a choice. It waits until either the next result is ready or the timeout has happened, and then it acts accordingly. So if we run this program, of course, it looks the same as it did before since everything finishes in 10 seconds. But if we shorten the timeout, we can see the select in action. There we go. The fast load's finished and we gave up on the slow load. Yep, and that time we managed to get them all done. If you've done any kind of parallel concurrent network programming, you might want to think about how the tools you use compare to this program. In particular, notice that there are no condition variables, no select loops, no epoll, no kqueue, no callback functions, no semaphores, and not a mutex in sight. In the runtime, of course, these things exist, but the abstractions here mean that your code can focus on the job at hand and not these low-level details. So I said at the beginning that for me, Go is a fast, fun, and productive language. And I hope I've given you a sense of how Go's interfaces, Go's reflection, and Go's concurrency support all combine to create that experience, and I hope you'll try it yourself. Before I close, I want to say a little bit about Go the project, as opposed to Go the language. We released Go version 1, or just Go 1 for short, on March 28th of this year. Go 1 is the first stable version of Go, the first time that we're making backwards compatibility promises. If your program works with Go 1, it will work with Go 1.1, Go 1.2, and so on. There are actually two separate implementations of the Go language, and we coordinate them using a written spec. It's rare these days to have a new language defined by a spec instead of a single implementation. And furthermore, I should mention that the spec actually came first. The spec is not just a retroactive description of the first implementation. One implementation of Go we call the GC compilers, and they're derived from the Plan 9 compiler toolchain. That was the first implementation, the one that I work on, and the one I've been using in this talk. Ian Lance Taylor used the spec to write a second implementation, a front end for GCC, and we call that compiler GCC Go. That front end, by the way, is written so that it could be hooked up to other backends, and in particular, we think it would be possible to hook it up to LLVM, although no one has done that yet. The GC implementation runs on FreeBSD, Linux, NetBSD, OpenBSD, OS X, Plan 9, and Windows, on x86-32, x86-64, and ARM. The GCC Go implementation supports many of those, but also Spark, MIPS, PowerPC, and Alpha. It even runs on Solaris. And the Go project originally started at Google to create a great language for writing the kinds of programs we need to write at Google. But we planned from the very beginning for it to be open source, so that other people could use it for those purposes and other purposes. The project was started by 3 people, Rob Pike and Ken Thompson, who worked on Unix and UTF-8 and Plan 9, and Robert Griesemer, who worked on Strongtalk and later on the Hotspot JVM. Ian Lance Taylor and I joined them a few months later, and since then we've been joined by many other developers both inside and outside Google. And we did the first release of Go in November 2009 using an open source BSD license, and since then we've done all the development, design discussions, code reviews, bug reports, bug fixes, and so on public mailing lists. And to date we've had over 200 people outside Google contribute code, and some of them are very active contributors. The XML printing that I showed you was contributed by an external developer, and most of the operating system ports, in fact everything but Linux and OS X, was done by external contributors. And I'm personally very happy to work on open source, and I'm happy that we have such a great community of developers, and I want to thank them. If you want to learn Go, I recommend using the interactive Go tutorial at tour.golang.org. It introduces language concepts, and then it lets you write programs using them all in your browser without downloading anything. You can find more information about Go at golang.org. This is the point in the talk where I took questions. And there were many, many good questions, and rather than narrate them here, I've put up the questions and their answers as a blog post, which should be linked in the video description. If you have more questions, you can visit golang.org and click on Help, which will bring you to a page with links to the frequently asked questions list, the mailing list, the RSC channel, and more. Thanks very much for watching.